Okay, thank you very much. And my name is Xiaozhong Liu here, and I'm presenting this paper. And my colleagues Zhuoren, Zheng, and Jinjiong, and Hongxia, and Yao. And so this work is about a task-oriented genetic activation for large-scale complex heterogeneous graph embedding. As the other speaker already mentioned quite well, so there's a very different kind of a graph and which holding very rich information. So generating graph embedding can be very essential for a number of downstream tasks like a recommendation. Okay. So far there's so many different kind of graph already exist. So the basic idea for embedding is given a specific function here, and this function can be either supervised or unsupervised, and we can create graph embedding into maybe two-dimension or multi-dimension space and to encapsulate the key information from the graph node. But here I want to address three key challenges and which can be the motivation of our work. The very first one is heterogeneity of the graph. Okay, so like this graph show that there can be more than one type of node and more than one type of edge exist on the graph. So we know that when the graph is become increasingly heterogeneous, so the algorithm, the proposed embedding algorithm and other random walk algorithm can be more complex than the homogeneous one, right? And especially when the heterogeneity is increasing, and so the challenge, the embedding function can be more challenging. And the other is scalability. So here we list a number of key data set and benchmark data set. We pretty familiar, maybe. We often use those for experiment. But you can find for these data sets, the size of the node and the size of the edge can be pretty small, right? So in most of the time in the real world application, for the real world application, so the graph size can be fairly large. So that can so when we have a small graph, so the computational cost may be okay, but when the graph size become larger and larger, so maybe the performance and efficiency part should be compromised. And the third one is multiplex. So when we say multiplex, so the graph embedding algorithm can be task driven. So here I provide an example. This is a heterogeneous graph. So between three candidates, between three users, there can be different kind of relationship. Like if they ever go to the same academic conference, or if they ever read co-cited academic paper, or they watch some YouTube video together, something like that. So the problem is when we have a very different task, for instance, like a co-author recommendation. So we know that Tiana and Tom can be further away because they may not share the same academic interest. They may not share the academic interest, and vice versa. But because for the social recommendation and because of their relation difference, so given the very different task, the maybe the embedding result should be task driven, and which will tell not just the topology information but also tell the task information. Okay, so here you will find that in the general solution here may not be very ideal to address this task, about task-oriented recommendation problem. And so here we provide a solution. New solution is called genetic heterogeneous graph embedding. A genetic heterogeneous graph embedding, so which can automatically navigate the random walker to sample the context vertex concerning a target specific, maybe search or recommendation. So we can call that a node ranking task. So for accuracy reason on a very complex heterogeneous graph, not all the edge, this is our assumption. So not all the edge types are equally important for the target task. And the task-oriented edge type navigation function can be significant for graph representation learning. And for efficiency reason, it can be intangible to perform a complex inference on the entire graph, and the local mining on the graph can be more can be more important for like subtask. Subgraph mining can be more efficient. Okay. So here I'm gonna give some example here. So for instance, given the very complex graph here, so when we say the complex, it means the node number can be 1 million or more, and I mean large scale complex heterogeneous graph. When we say large scale, means the node number can be more than 1 million, and the edge type can be more than 10. Okay, so for instance, if we have such a graph, so then it can be a really good platform for the proposed algorithm, genetic heterogeneous graph embedding algorithm. So let's take a look at the algorithm framework here. Unlike the other existing methodology, so when we represent the graph, the heterogeneous graph, so because we may have more than 10 different kind of edges, so that's the reason for each kind of edge. So we use 0 or 1 to represent whether this edge type being selected or not being selected. Okay, so 0 means this one is being ignored. This type is being ignored for the target task. And 1 means this edge type is being selected for random walk for the given task. So that's the reason we use in the very first step. We use a genetic algorithm instead of the other optimization algorithm like a gradient descent for this activation, for this genetic evolutionary activation. Okay, the good part is for genetic algorithm, we only have for each edge type, we only have 2 different states, either 0 or 1, select or not select. So we can randomly initiate a number of solutions, and by using genetic algorithm and by using evolutionary activation function, and eventually, hopefully, we will evolve to the best solution for to activate the most significant edge type and ignore those unimportant edge type given a specific task. And so the second part will be even better. That's another key reason why we use a genetic algorithm, because when we use 0 and 1 for edge type activation, so the graph actually being the graph size being reduced significantly. Okay, because we select some edge type and ignore some other edge type. So that's the reason this some edge really disappear on the graph. Okay, so those edge really disappear on the graph, which means the size of the graph, the topology of the graph can be significantly reduced for random walk. Okay, so that's the reason at the second step, we have a much smaller graph compared with the original one for random walk function. And then for the third part, so then when we really generate embedding, when we use skipgram to generate embeddings, our graph size can be much smaller. Okay. And so in sum here, we create something called edge type activated vector. So this is for each dimension, it represents one specific type of edge, and we use 0 and 1 as the activation state as the activation strategy. Okay, so the goal here is we preserve the critical edge types and removing the noisy ones. Okay, given a specific ranking task. So here we know that given the very same graph, when the task is different, the activated vector can be quite different. So let's talk a little bit about why binary, where instead of using the other classical optimization method. So here we really want to balance and compromise the optimization performance and efficiency part. Okay, number one is not all the edge types are equally important given the target task, right? So some edge can be really important while the others are not very important. But number two, it could be very time consuming to learn the edge type fitness distribution given the target task. We have a couple papers earlier talk about how to learn this edge type usefulness usefulness distribution as a probability distribution. But the problem is this cost, for instance, when we use a gradient descent, the cost can be fairly large. So which can be impossible for very large scale graph, and especially when the edge type number is really large. Okay. And the size, essentially we want to address number 3. The size of the graph could be further reduced when we use just 0 and 1, because 0 here is not a tiny score, it's 0. 0 means we just remove this edge from the graph. Okay, so then the random walk efficiency can be really, really high. So for genetic algorithm, we have to have a fitness function, which is a genetic activation strategy. So let's take a look at genetic algorithm a little bit more. So when we compare two different kind of optimization method, one is gradient descent and the other is genetic algorithms. Let's take a look at their difference here. So number 1 is the computational cost for gradient descent. It can be decided by the target optimization function, which is always kind of expensive for very large scale graph embedding. Okay, but genetic algorithm define a fairness function to estimate the relation strength given the target task, which can be much more efficient when the graph size is very big. Okay, and the second reason is genetic gradient descent is not directly targeting to find the optimal edge type activation vector. Okay, but the genetic algorithm is able to learn the optimized solution in the search space. And number 3, gradient descent may start in the local optimization. Of course, there's some algorithm, there's some solution to address the local optimization problem, but which cost can be even higher than the classical gradient descent algorithm. Where genetic algorithm itself can be quite efficient to deal with this problem and to achieve the global optimization problem. And we know that when the graph size and is very big and the graph edge number is fairly large, like more than 10, so then the global optimization can be really important. Then let's talk about the genetic activation strategy, like the fitness function, what it looks like. We propose 3 different hypotheses and then generate 3 different functions, fitness functions to address different hypotheses. So let's take a look one by one. The first one is greedy algorithm. So if you're interested in, you want to find more algorithm detail, you can read the formulas inside of the paper. Okay, so but here, the greedy part means this is based on a very straightforward hypothesis. So when the vertex has more neighbors, tend to have stronger connection. For instance, given the specific task, so let's say that A and E is a labeled pair of vertex. Okay, so they should be connected together. So like A and E, we already know they're friends. Okay, so we want to, so this is a friendship recommendation. So we want to predict that A is a friend of E or E is a friend of A. So that's one piece of training data. And then based on the greedy assumption, we hope that the A will have the node A will have more neighbors and E will have the more neighbors. When they have more neighbors, they have a better chance to be connected. So A will have a better chance to random walk to E. Okay, so let's say that we have maybe 2 different solutions. We have 2 different genetic solutions. The first ones we activate a graph like this one. The second we activate a different topology like the second one. So here, because A has more connections, A has more neighbors, and E has more neighbors, so we simply believe that the second solution can be better than the first solution. So that's the greedy activation strategy. The second one is based on refine. So that's another different hypothesis. It's based on this refine function. And the assumption is that this is based on if the node has some shared neighbors, and the neighbors do not have many relationships, do not have other, really have other kind of relationship, then we believe this graph topology can be strong. Okay, so for instance, like this, the first graph, so A and E has one shared neighbor, which is B. Okay, but the second one is the same thing, right? So A and E also share the very same node B here, but the difference is B here has two different connections. Well, in the second graph, B only have another one extra connections, except for A and E. Then in this case, we assume that the second graph can be more important because A and E can be better connected because E is like work as a stronger bridge to connect A and E. Okay, so in this case, we assume that A and E should be have a better chance of random walk to each other. So the fitness of second graph is better than the first graph. The third one is a little bit more complex because the first two actually based on the node, but the third one is based on the edge. Okay, so this one is we want to calculate the importance of the connections. Okay, it's a little bit like a random walk. So with the function proposed by the weight the important edges, not the node anymore, to the common neighbors more heavily. Okay, like we have B here, then we want the edge, we want to select the most important edge to interconnect A and E here. The difference for the first two function is based on node selection, but the last one is on the edge selection. So we found that when we have edge selection here, actually we find the most important edges. So we know that this one, the very last one, the edge one, is more aggressive than the other. It have a really good chance to significantly reduce the size of the graph. Okay. All right. So another one is the good news for this algorithm is it can be quite transparent. This algorithm can be quite transparent to the other embedding techniques. So this method is more serve like a plug-in, right, for the other kind of graph embedding algorithm. If you're interested, you can read our algorithm in the paper. But the good news is what our algorithm is more like a plug-in. So whenever you have another embedding algorithm, you can just plug in our algorithm. Okay, so because our algorithm really, what it really learn is an edge type activation function. So it can intuitively work with any other kind of embedding algorithms, no matter this algorithm is designed for homogeneous or heterogeneous. Okay. So for and then for the activated random walk, so that can be a two-step thing. The first one, we draw a probability distribution. We draw a edge type from the edge type collection, and then based on this edge type probability distribution, even though this is just 1 or 0, but this is still distribution, and we can really sample the edge. So based on this edge type distribution, we can sample the edge for the actual random walk and generate the final embedding. So we're gonna skip this part. This is the activated heterogeneous skip graph embedding. So this part can be we use also negative sampling. So that's a little bit like a classical study. So this is our data set. We use two different data sets. Once again, the proposed algorithm is designed to address large-scale complex heterogeneous graph. And so we choose two different data set. One is scholarly data set with like citation, papers, authors. And the other one is we're gonna have e-commerce data set. Okay, so for the first one, I mean, both one can be fairly large. It's more than 1 million nodes. But for the first one, we have a 3 type of node, and we have 8 type of node for the e-commerce one for the second one. But the edge type is really large. So we have 10 different edge type for the scholarly graph, where we have 22 different type of edges for e-commerce graph. Okay, so so when we create activation function for the graph for the edge type, so here, for instance, for 22, we create a size equals 22 activation strategy. I mean, each one, this can be 0, 1, 0, 1 to represent either, whether the target edge type being selected or ignored. So this is our experiment readout. So we use MAP, NDCG, because this is for ranking, okay? So MAP, NDCG, precision, and MRR to evaluate performance of the ranking. And so for scholarly graph, we use two different tasks. The first is citation recommendation, where the other one is co-author recommendation. Okay, and for the e-commerce one, we use a feeds recommendation for the e-commerce data. So here, the interesting part for the scholarly data, even we have the very same graph as we said, even we have the same graph with the same topology, but when the task is different, so the activation outcome should be different. So we compare with a number of state-of-art baseline algorithm, including some homogeneous homogeneous graph embedding method like a line or node-to-WAG, and also with some other heterogeneous graph embedding mechanism like a MetaPath-WAG. Okay. So, and we compare three different our method, germ algorithm, with three different hypotheses: greedy, refine, and the edge. Okay, so this will be a three. So we have always three different kind of experimental algorithm for comparison. So for efficiency, I'm sorry, I didn't say that. So most of the time you find that the performance of our algorithm is most of the time performance can be pretty good. Okay, can be pretty good, and most of the time it can successfully enhance the accuracy of the recommendation, like precision, MAP, and MRR, so which is pretty good. But more importantly, let's take a look at the second one. So the second one is to tell the computational cost for each algorithm. So you will find that the original algorithm, the task, you will find that the edge, the type, the number of nodes and the number of edge can be fairly large. But when we apply the proposed algorithm, so eventually you will find the node size really decrease, while the edge size also really decrease. So once again, we say when we use edge selection, because it's based on edge selection, so it's really aggressive. So the node edge size really decreases significantly. But the other two, like greedy or refine, is also somehow decrease the graph size. Okay, same thing for all the tasks. So we know that the computational cost will be much smaller. So this graph visually present how likely the computational the running time empirical running time comparison. So the first bar is the when we use the original algorithm like a node-to-WAG or deep work. But when we apply our algorithm, so you will find by using this activation function, because the graph topology really changed. So that we remove some edge type, and so that's the reason that the running time really decrease. Okay, so the most aggressive one, like when we use the edge selection, and can decrease about 80 to 90%. So for the running time, also we have some comparison, because we have we have three part of the algorithm, right? The first part is genetic activation, the second part is random walk, and the third part is graph embedding generation. So you will find that most of the cost here is actually focusing on the graph embedding generation. Okay, but the other two will account for about 20% or 30%. So it's not the major cost of the algorithm. So that's the reason we say we have a confidence that our algorithm, when as a plug-in, go work along with the other algorithm, the performance can be pretty good, because most of the cost, computational cost, is focusing on the embedding generation part. Okay, and so we have some. This is a little bit like ablation test. So when we have the edge type activation or without it, we have some comparison. Okay, so you will find the performance really increase while the cost decrease. So which means this algorithm can be quite effective to deal with a very complex heterogeneous graph. And for parameter tuning, if you're interested in one, again, you can refer to the content of the paper, but you will find that because for a genetic algorithm may have a crossover read and a mutation read. So you will find that the performance is really flat here. It's really flat here. So which means those parameters for genetic algorithm can be not very sensitive for the performance of the embedding quality. The very last visual is I show you at each iteration you will find it. So originally, if we select everything, all the nodes, all the edge types. So after several iterations, like 16 iterations, so we already be able to select some very significant. We already be able to select some very significant edge type. While the unimportant ones will be just ignored. And overall, the trend is the edge type size is decreasing. Okay. All right, so let's make the conclusion. So we propose a new solution, Zhuoren, to address challenging heterogeneous, very large scale heterogeneous graph. Okay, and more importantly, this is task driven. Okay, this is task driven. So for different tasks, the proposed algorithm can efficiently preserve both the structures and semantics of that heterogeneous graph given a specific search or recommendation task. So a genetic solution this algorithm is based on this activated heterogeneous skip graph framework, and it can be a really nice plug-in to the other existing graph embedding algorithm. So we're not trying to replace existing algorithm. Instead, we provide a nice plug-in to empower the other algorithms, embedding algorithms, to address a complex heterogeneous graph. Okay, and more importantly, the proposed algorithm can significantly reduce the running time and will even, without sacrificing, even improves somehow the performance, the recommendation and the ranking performance. Okay. Thank you very much. That's all for our work. And if you have any question, please feel free to shoot me an email. Okay. Thank you very much.
Thank you for your presentation. Once again, we will have like the question answers at the end, answered at the end of the session. So if you have any questions, just type them in the chat box. The next talk is a pre-recorded talk, but the authors are here and they will answer the questions at the end of the session. The next talk is on